right, good afternoon, everybody. I'm just finishing my lunch. All right, how is everyone? Good, good. Awesome. Cool. All right, so hopefully everybody has turned in their homework. Um, I'm going to grade that between now and Wednesday, give you some feedback on Canvas, and then Wednesday we can talk about specific things that I found that seem to be major issues and so on and so forth. So, unless you have urgent questions on homework 2, I'd like to hold off on talking about that until Wednesday after I've had a chance to look at it. And then we can go through the details of it then. I'd like to start by looking at your next homework, homework 3, which is posted on Canvas now. So these are more questions from chapter 3, so we're continuing to talk about logic and propositional logic, propositional calculus this week. So more homework from chapter 3. So section 3.4 number 2, section 3.5 numbers 2, 4, and 6. And let me just pull up the textbook. So 3.4 number 2, so you're looking at a fallacy, something which is not true. And a general statement which is mentioned in Canvas in the homework, when you see something like this, okay, where there's this double arrow in the middle, what it basically means is that all of this stuff to the left of the double arrow implies this stuff to the right of the double arrow. Okay, so you can interpret this as saying if this is true, right, if this conditional statement is true and not P is true, then not Q is also true. Okay, and this turns out to be a fallacy. There are cases for certain propositions P and Q where if P then Q is absolutely true, and where P is absolutely false, but it turns out that not Q is also false. So one way to demonstrate that this is not a law of logic, find a counterexample. Find a P and a Q for which this left side is true, but the right side is false. And we know if this is true and the right side is false, then if left side then right side fails to be true, right? In which case this is not a law of logic. So question 2, you're just looking for a counterexample. All right, 3.5, we're digging into actual proofs. So 3.5, question 2 says prove with truth tables. Okay, here again, we have things on the left of this double arrow, and they're separated by a comma. The comma is taken to be a logical and. Okay, this is written out in Canvas. This statement A is saying if Q is true, and if not Q is true, then P is true. All right, prove that with a truth table, and notice we don't have anything about P on the left side of this. That's okay. Write a truth table with 2 input variables, P and Q. You're going to have 4 rows for the 4 possible combinations of P and Q's truth values. And for each of those, look at the value of Q, look at the value of not Q, look at the value of both of those being true, look at the value of P, and see if the statement Q and not Q implies P is true or false. And you should find that it's true in all cases. Part B, similar thing. Pick P, Q, and R and calculate if P then Q's truth value for each of those 8 possible conditions. Calculate the truth value of this right-hand side for each of those 8 possible conditions. Show that if the left side is true, then the right side is true. All right. This will deviate from intuition pretty severely. Okay, you want to, for this, try to think about just the low-level propositional operations that you're doing. Okay? If you rely too much on intuition, it will not make sense. Okay, so this is a fairly mechanical problem. Question 4, give direct and indirect proofs of these three theorems, these three statements. Okay, again, given this, and this, and this, we should be able to conclude that. Okay, that's what part A says. We're going to do proofs all week, but our proofs are going to basically start off with things that we are given. We're going to take those as being true, and we're going to try to prove that this conclusion is true. And we're going to learn two basic classes of proofs, direct proofs and indirect proofs. For each of these three questions, you want to do a direct proof and an indirect proof. So question 4, you're going to write out a total of 6 proofs. Make sure it's really easy for me to follow. What I would like to see is 4A direct proof, 4A indirect proof, 4B direct proof, 4B indirect proof, 4C direct, 4C indirect, right? But whatever order you do that in, make it absolutely clear what I'm looking at. Okay, direct or indirect proof of A, B, or C. And we'll be doing these all week, so we'll get a lot of examples of this. And then question 6 is just a standalone question, which states a number of hypotheses and then draws a conclusion and asks you to decide if this is a valid argument or not. If it's a valid argument, you should be able to prove it. If it's invalid, you should be able to find a counterexample. So up to you which one of those to pursue. Alright, so that's homework 3. It's due a week from today. Alright, on to rules of inference. So this is continuing the stuff on pages 58 and 59. Page 58 was these laws of logic that we played around with last week. And these were sort of analogs to stuff that we did in 250, right? Double negation and De Morgan and identity laws and so on. Those all work with plain old logic equations in Engineering 250, digital logic. Table 59, common implications and their equivalents. Okay, so these are the rules we're going to use to do very formal proofs. And they have fancy sounding names like disjunctive simplification and conditional equivalence and so on. But we're going to dig around with these and use them to prove things in very rigorous ways. So first thing to think about is, what are we proving? We're going to write a lot of statements down, and we're going to discuss them, and we're going to develop proofs, or in some cases disproofs, of these things. But it's a good question. What are we really proving? Because what do we really know? And the answer is usually not a whole lot. And so let me start with kind of a classic example. Here's a proposition. If it is sunny, then I am running. I'm out for a run. Or I'm being chased by the sun. If it is sunny, then I am running. That's a proposition. It has a truth value. Since the sun is out right now and I'm not running, we can suppose that this is a false proposition. But we don't necessarily know that. Okay, all we know is that this is a proposition. It is sunny. That's another proposition. We happen to know, if we have a window to look out, that this is a true proposition. But you're in a different part of town, maybe it's a false proposition where you are. But it's a proposition. It's a declarative statement that has a truth value. We don't know if it's true or not. So we have two propositions. We don't know if either one is true or not. Here's what we do know. If we are told that both of these propositions are true, then the following proposition is also true. The proposition, I am running. All right, this is key. We're given two propositions. We don't know if they are true or not. We're given a third proposition. We don't know if that's true or not. What we can prove in this course is that if these first two propositions are true, then this third proposition is also true. That's really the best we can do. We're not going to learn anything in this course that will let us know if it's sunny or not. Or will let us know what my secret training schedule is, if I run in the sun or I run in the rain, or I don't run at all. Okay? Those things are outside the realm of propositional logic. But what we can absolutely say is, if this is a true statement, if that's a true proposition, and this is a true proposition, then this is also a true proposition. And that's the kind of thing we're going to be working with this week. Ways that we can take certain propositions, and by knowing that they are true, we can absolutely ascertain that some other proposition is true. All right, so what does this look like? So let P be the proposition. If it is sunny, then I'm running. Let Q be the proposition. It is sunny. Let R be the proposition. I am running. All right, what have we just said? If P is true and Q is true, then R is true. Regardless of what P, Q, and R might be. Oh, let me back up a little. Forget that. Let me start this. All right, let S be the proposition. It is sunny. Let R be the proposition. I am running. Okay, if we are given that this is true, right? Because our first proposition I said was, if it is sunny, then I am running, and we're saying, let's suppose that that is true. So given that if S, then R is true, and given that S is true, right, that was our second statement, it's sunny, I said we can conclude that R is true, I am running. So given that S implies R is true, and given that S is true, then R is also true. All right, that's our game plan here. So what does this look like in the language of propositions? If this is true and S is true, then R is true. And we might draw a double arrow here to make sure we understand that it's this stuff over here that implies that thing. All right, we could also use parentheses. All right, this is a theorem. This theorem is saying if this is true and that is true, then this is also true. The claim is if we start off with just the knowledge that this statement is true and that statement is true, we can eventually construct a convincing argument which shows that this statement is true, R. And a lot of times we write this differently. We could write it like this. Okay, what does this mean? The stuff above the line are things that we are given. So given that these propositions are true, the horizontal line can be taken to mean therefore, and the thing written below it means that this is also true. So something like this is a statement of a theorem which says if this is true and that is true, then also the thing below the line is true. And so when we're asked to prove, for example, these questions in section 3.5, give direct proofs of and let's just look at part A. So part A says if P then Q is assumed to be true. Part B says if not R then not Q. The third part says not R. And the claim is from all of that we can conclude not P. So we could write that symbolically like this. If P then Q, if not R then not Q, not R, therefore not P. And that's a theorem which says if you know that these three things are true, then you're guaranteed that this thing is also true. So those are the kinds of theorems we want to prove this week. Given a set of propositions being true, we can conclude some other proposition. And one more time, let me just emphasize, we don't know whether S is true or false. We don't know whether R is true or false. We don't know whether S implies R. These could all be nonsense. They could be things that are absolutely false. S could be your teacher knows how to fly by flapping his arms, right? Regardless of what those propositions actually say and regardless of whether they're true or false, what this is claiming is that if this is true and that is true, then R is true. All right, so how do we prove these? Well, we use these rules of logic. So page 59. Logical implications. And the first logical implication we find is something called detachment. Detachment says, given that P implies Q and given P, we can conclude Q. Well, that's exactly our situation here. We're using S and R instead of P. But basically we're told that S implies R, we're told S is true, therefore we can conclude R is true. Now this should make intuitive sense, because regardless of what S and R might stand for, here's what is happening. Suppose we are told that it's absolutely true that if S is true, then R is true. We're being told that that's a true proposition. So now we can say if S is true, R has got to be true. And now we're told, oh, and by the way, S is true. Well, if we believe that if S is true, then R is true, and we believe that S is true, we have to believe R is also true. Because we just said S is true, and if S is true, R is true. So these two guarantee to us that R must be true, so that's our conclusion. All right, these things above the line, these are hypotheses. What are hypotheses? They're assumptions. They're things that we're assuming are true without proof, without cause. This thing below the line, this is the conclusion. All right, why do we want to do this? We can prove things with truth tables, right? But truth tables get really big really quickly. So let me give you an example. So here's a pretty long theorem. If A implies B, and B implies C, and C implies D, and D implies E, and so on and so forth, and Y implies Z, and we are told that A is true, then we can conclude Z is true. Now logically this makes sense to us, because if we know that A is true and A implies B, that tells us B is true, and we're told B implies C, that tells us C is true, and we're told C implies D, that tells us D is true, and if we continue down another 22 lines, we'll find that Y is true, and Y implies Z, that means Z is true. So we can prove this in, 27 or 28 lines of a proof by repeatedly using this property here, right? This property that we call detachment. So 26 or 27 applications of detachment combined with this, and we can prove that Z is true. If we try to do this in a truth table, we're going to have a truth table with 26 variables in it, A through Z, and we're going to have to list all possible combinations of truth values for those. That's 64 million rows of a truth table. Okay, that's not something we want to try to fill out. It's totally not practical. So truth tables are kind of a almost mindless approach to proving things. The fact that they're mindless, they don't require a lot of inspiration, makes them really good for computers to do. Right? If we want to do automated theorem proving, we'll probably do it using truth tables. But the things that are easy for computers to do, that are mindless for computers to do, can be really hard for humans, because we're not good at manipulating 64 million things times 26 columns, whereas a computer doesn't have much difficulty with that. All right, so let's take a look at some of these rules of logic. So detachment we've been talking about. If P then Q and P, we can conclude Q. Okay? There's a flip side to that, which is called indirect reasoning. So what does indirect reasoning look like? So indirect reasoning says the following. Given if P then Q, and given not Q, we can conclude not P. And that's guaranteed. Okay, why does this make sense? If P is true, then Q is true. We firmly believe in our minds that is absolutely a factual statement, right? It's a hypothesis, so we can assume that's true. We also believe absolutely that Q is false. Is there any possible way, given these two statements, that P could now be true? And the answer has got to be no. Because we understand direct reasoning or detachment. If P is true, then Q is true, but we're told Q is not true. So there's no way P can be true. Well, if P is not true, what do we conclude? P must be false. So not P is true. So this is indirect reasoning. And it's probably our second most popular rule of inference. Let's see, question. What would happen if we were told P was not true? All right, suppose we're told if P then Q is true, and we're told P is false. What can we conclude? So we're told if P then Q, and we're told not P. Can we conclude anything? We know Q is true or false. Can we tell anything about Q beyond that? And the correct answer is nope, you cannot conclude anything. Right? So P could be the proposition that I am fabulously rich. And Q could be the proposition that it's sunny outside. And I can guarantee you I am not fabulously rich. But can we conclude anything about whether it's sunny outside or not? No. P could be the proposition, it is Wednesday. Q could be the proposition, we are in CSE215. If it's Wednesday, then we have CSE215. It's not Wednesday. Does that mean we're not in CSE215? Not necessarily. So this is called a fallacy. This is actually called the fallacy of denying the hypothesis. And it's a common mistake in logical reasoning. And it pops up a lot. It pops up a lot in daily life. So if I hang a flag outside my window, then I must love the United States. I do not have a flag outside my window. Can we conclude that I don't love the United States? Well, no, I'm not allowed to put a flag outside my window because I live in an apartment. Right? But there are people who will say, well, not P, therefore not Q. Right? This pops up all the time. There's another fallacy while we're here. If P, then Q, and Q, therefore P. And that's also a fallacy. Right? If I win the lottery, then I'll continue to teach at Clark. I'm still teaching at Clark, therefore I must have won the lottery. Makes no sense. So this is called the fallacy of affirming the conclusion. So we'll play with fallacies in a little bit too, but that's just the flip side of detachment and indirect reasoning. All right, so indirect reasoning, detachment, those are valid laws of logic. Those two fallacies, very, very close to these, but fundamentally not laws of logic. All right, disjunctive addition. So this is a funny one. Given P, we can conclude P or Q. And there's nothing here that says anything about Q on the left side. So disjunctive addition says given P, we can conclude P or Q. Yeah, sorry, back to the name. So this is the fallacy of affirming the conclusion, because what we have is a conditional statement and we're supposing the conclusion is true, it's affirmed, and we come to a fallacy. This first one, we have a hypothesis implies conclusion, and we deny the hypothesis, and that leads to a fallacy. So this is the fallacy of denying the hypothesis. This is the fallacy of affirming the conclusion. And we will go through those again in more detail. All right, disjunctive addition. Given P, we can conclude P or Q. Well, that might seem a little weird at first, but for example, let P be the proposition 1 plus 1 equals 2. Let Q be the proposition dogs can fly. This says if we know that 1 plus 1 equals 2, then we also know that 1 plus 1 equals 2 or dogs can fly. Well, this is a true statement, right? Regardless of what the value of Q is, we know that this is true because we know P is true. And as long as P is true, P or anything is also true, even if Q is absolutely false. In fact, P or false is true if P is true, because this is exactly the same thing as P. So this is a rule which we can use sometimes to add stuff to our expression, right? If we know that P is true, then we can conclude P or Q is true, where Q is anything. But sometimes adding more stuff to an expression makes it possible to do something else, like factor something out, or apply De Morgan's theorem, or do some kind of simplification. So sometimes disjunctive addition will come in and be handy. All right, conjunctive simplification. So disjunction is the or, conjunction is the and. And conjunctive simplification basically says P and Q implies P. So the way this looks as a formula is, if we know P and Q is true, then we know P is true. And similarly, if we know P and Q is true, then we know Q is true. And this is absolutely true, because the only way that P and Q can be true is if both P and Q are true. So if we're told P and Q are both true, we can absolutely say, oh, I guess P is true, right? I mean, it's basically the definition of a conjunction being true. And if you promise me that P is Q and P and Q is true, then I'm safe in assuming that Q is true. So these are like the axioms of algebra, for example. They're things that we will take to be true, and we will use them to prove other things that we don't necessarily know ahead of time to be true. So they're the building blocks that we're going to use. All right, so there's more of these. Disjunctive simplification. P or Q and not P implies Q. And the second one is just using Q instead of P. P or Q and not Q implies P. So what does that look like in our vertical theorem notation? We're told P or Q is true, and we're told P is false. Q must be true. Why? Because this first statement says that at least one of these must be true. This second statement says the first one is not true. Well, then the second one must be true. That's Q. And similarly, if we're told P or Q is true, but that Q is false, then P must be true. So that's another simplification. All right, chain rule is really handy and usually pretty obvious. Given that P implies Q and Q implies R, then we can conclude P implies R. And why is that? Well, if P implies Q, then if P is true, Q is true, and if Q is true, R is true. So if P is true, R is true. Well, that's what this conclusion says. If P is true, then R is true. So you can work your way through. So good old chain rule works for us. Conditional equivalence. This is an oddball. Conditional equivalence says the following. If P, then Q is logically the same thing as not P or Q. And this we can prove using a truth table. And we have to remember what the truth table looks like for a conditional statement. Basically, if the conclusion is true, the conditional is true. If the hypothesis is false, the conclusion is true. But the conditional fails if the hypothesis is true and the conclusion is false. So that's the only time the conditional is false. On the other hand, if we expand this side of our equivalence, negation of P would be true, true, false, false. And so a negation of P ORed with Q, well, if the negation of P is true, then it's true. If Q is true, then that OR will be true. But in this row right here, negation of P is false, and Q is false, so the OR is false. And now we simply observe that this column and that column have the exact same truth values in all cases. That's enough to say that this is equivalent to that. And this is not an implication, this is an equivalence. This implies that, and that implies this. So they have to have exactly the same truth values, right? We've also written this as an equivalence sign. But this means that if we have an if-then statement like this, we can replace it with a disjunction. Or if we have something in this form, we can replace it with a conditional statement. And depending on what else we're given in our proof and what else we've written down so far, it may be useful sometimes to switch from this to that or the other direction. All right, so these are our building blocks. All right, biconditional equivalence just goes both ways. Contrapositive is another equivalence, and we've talked about this one as well. But let's do this one more time. So if P, then Q is the same thing as if not Q, then not P. And we can show that with truth tables pretty easily also. But logically, what is this saying? Suppose we're told if P is true, then Q is true. We can also say equivalently, if Q is false, then P is false. And why is that the same thing? Because if Q is false, and we know that if P is true, Q is true, P has got to be false. If Q is false, there's no way P can be true. Why? Because if P is true, Q has to be true. So if Q is false, that's enough to conclude P must also be false. All right, so this is your contrapositive, and that's going to pop up in a lot of proofs. All right, any questions so far? So we want to start using these things and try to do some proofs. And this is like simplifying expressions by using those identities. It's kind of a game. It's a trial and error. It's getting yourself familiar with these building blocks, these tools, and developing an intuition for when should I apply what. When should I try to make something simpler? When should I make it more complex? So let's do some examples of proofs. So let's pull one of these out from the book. So we'll do example 3.5.3, which says if P then R, if Q then S, P or Q, and therefore S or R. All right, so here's the theorem we want to prove. If P then R, if Q then S, P or Q, therefore S or R. So we're allowed to assume these three statements are all true. These are true propositions, and we're trying to conclude this. So think about that for a minute. Think about these rules of inference. And what kinds of things might we be able to do to get to this conclusion? So think about that for a minute or two and start posting some ideas in chat. Any ideas? Yeah, let me pull the book back.
notation might be useful when we're looking at with a P then R, if P then R, and then at the bottom we have that ANDed, with P or Q.
Mm-hmm.
We somehow remove the Q or not need to look at it somehow. I don't know what we'll do with that yet, but then we could probably just look at it as just R.
Okay. So you're describing something that I think is logically sound, right? I mean, we know that if P is true, R will be true. We know that if Q is true, then S will be true, and we also know that either P or Q is true. So there's two possibilities. If P is true, well, then this gets us R, and if Q is true, then this gets us S. So we're going to get either R or S, right? So this is believable. But it's not clear how to sort of formalize that notion. So somebody suggested disjunctive addition for P or Q. So if we know that P is true, we could conclude P or Q. But we're actually given P or Q, so some kind of simplification might help. But we're already told P or Q. We could OR that with something else. So somebody else suggested conditional equivalence. So what could we do conditional equivalence on? Part of what's going on here is we have two if-thens, and then we have a disjunction. We have an OR statement. And most of these things combine, conditionals with one term, or combine multiple conditionals like a chain rule, right? So what if we did conditional equivalence on P or Q? So P or Q is equivalent to, well, what does conditional equivalence say? It's equivalent to, if not P, then Q. Now we need to sort of think about this a little bit. Something or something else is, or if P, then Q is the same as not P or Q. So if this thing, then that thing would be the equivalent to the negation of this thing, or Q, which is just P or Q. And so this is a common form of conditional equivalence where we'll use. So this thing is equivalent to if not P, then Q. And my inner monkey gets excited when I see something like if this, then Q, and right here I see if Q, then something else, because you can combine those, right? You can turn that into one thing. So I could put this together to get if not P, then S. Well, there's nothing I can directly combine this with, right? Because I don't have an if S, then something else. But I have a P right here, if P, then R. And I have a not P here. Can I put those together somehow? Well, we also have this contrapositive. And if you have if-thens that you'd like to put together, but they don't quite line up right, particularly if you have two things on the same side and you'd like to have them on opposite sides to chain rule them, contrapositive might be what you need. So this is going to be the same thing as if not S, then P. And now this and this can go together with the chain rule and say if not S, then R. Well, that's starting to look really close to this, right? We've got S and R together. Thank you. All right, we got not P implies S. We could take the contrapositive and say not S implies P. And now this and this can go together and say not S implies P, P implies R, not S implies R. And that's starting to look really close to this, S or R. We've got the two terms that we need. Is there some way to change this to get that? And the answer is, yeah, that's one more conditional equivalence. So here we've got this thing implies that thing. Conditional equivalence says that's equivalent to the negation of the first thing, ORed with the second thing, which is just S or R. All right, so now we have convinced ourselves, perhaps, if we believe what we've been doing, that from these first three statements we can get to S or R. This is not something you want to turn in, okay? This is not a proof. This is a rendering of your thought process, okay? But that's not a proof. We need to formalize this. So let's take that and let's turn it into something like a formal proof. And then we'll do some more of these that will be probably more straightforward. So first thing I'm going to do, I'm going to state what I'm trying to prove. Prove if P then R, if Q then S, P or Q, all taken together implies S or R. And you always want to state in the beginning of your proof what you're trying to prove, right? Because your goal is, you go up to a stranger on the street, you hand them this piece of paper, they can read through it, nod their head, and say, yep, I guess you're right. All right? So you're going to start off with, what are we trying to prove? Given this, and this, and this, then that. Or they call the police, right? All right, so how do we do this proof? Well, we are allowed to assume these three things. So I'm going to start off by writing down those three things. Sometimes you've got a red herring. Sometimes one of these things will have nothing to do with your proof. It's just thrown in there to trip you up. But I'm going to just write down these three hypotheses so that I have them in front of me and I know that I can use them. So I'm going to number each statement that I write, and each statement is going to be a proposition. That's really important. Everything I write here has got to be a proposition. So first thing I'm writing is the proposition if P then R. And everything I write here has got to be a true proposition. Okay, why am I saying that if P then R is a true proposition? It's a hypothesis. All right, so every proof you write, you're going to start off by saying what you're trying to prove, and then you're going to write a series of lines, and each line will have three pieces to it. A number, the proposition itself, and the reason why that proposition belongs in your proof, the reason why you know it's true. So the first line of my proof says if P then R, and that's true because it's a hypothesis. The way we're proving this is by assuming the three hypotheses are true, and then using these rules of inference to conclude S or R. So that's a hypothesis. Line 2 is going to be another hypothesis. And line 3 will also be a hypothesis. All right, line 4, what did we do? We used conditional equivalence. We know that P or Q is true, because that's a hypothesis. And we have this thing called conditional equivalence, page 59 of the book, which tells us if P or Q is true, then this is also true. So I can validly write this down as part of my proof. Why? Because I used conditional equivalence on statement 3. So anybody reading my proof knows why this is here. They just look at statement 3, they know what conditional equivalence is, they apply it, and they say, oh yeah, okay, so if not P, then Q. That must also be true. Step 5, we're going to use the chain rule. We're going to say if not P, then Q, and if Q, then S, and so if not P, then S. The reason for that, chain rule, combining 4 with 2. All right. And then we said that we wanted to somehow combine something with this. And we had the idea if we took the contrapositive of this, we would end up with this, and that would go together nicely with the chain rule with that first statement. So we want to put this as part of our proof. So that's going to be our next statement. Not S implies P. Why can we do that? Contrapositive. Applied to step 5. And then we have another chain rule. We could put this together with statement 1, and we could get if not S, then R. That's the chain rule, 6 and 1. And then not S implies R. Conditional equivalence tells us that's the same as S or R. So I can write down S or R as now being known to be true. And that's conditional equivalence applied to statement 7. All right, what do we have now on this piece of paper? We have a statement that we are trying to prove. We have the 3 hypotheses written down, and then for reasons that are logically sound, as illustrated in this column, we have another series of statements which are each known to be true, ending with the statement S or R. We have just proven that given these 3 hypotheses, S or R is true. Well, that's what we were asked to prove. Right? That's what this statement says. Given this and this and this, prove that. Well, we have done that. We've just proved that S or R is true. That's the end of our proof. So we can write QED, which is what was to be proven, and our proof is done. And that's a perfectly formal, completely detailed, irrefutable proof that given these 3 things, then that thing is also true. Now, getting there takes trial and error, right? So you work on scrap paper, you play around with things, you try biconditionals, disjunctive addition, conditional equivalence. It's a lot of trial and error. That trial and error process is how you learn to do this, okay? You've got to try to use the contrapositive in cases where it works, but also in cases where it doesn't help. Right? You've got to try to use conditional equivalence in cases where it simplifies things, but also in cases where it makes things more complex. You're developing an intuition, a feel for what these different rules of logic will do to different kinds of propositions. And you're developing a sense, a feel for, well, here's a P implies R, here's a Q implies S. Those don't go together. I got to find some way to either link P and S or Q and R, right? And how can I do that? And sort of working through like that. So it's like, factoring polynomials. You got to learn that a 6 can be written as 2 times 3, and 2 plus 3 is equal to 5. So when you see a 6 and a 5, you start thinking of that factorization, right? It's just practice. Trial and error. All right. But once you've done this on scrap paper and you sort of see the pathway, then you need to formalize it. And this is what you turn in. This is what you put on your exam, right? This is what you hand to the stranger on the street. And it's irrefutable, right? And every step is documented, and the reason for it is spelled out using these things from, a well-established list of reasons. So conditional equivalence, what is that? Oh, that's this thing right here, right? So you don't want to put reasons like this just makes sense, or this follows logically, right? Because maybe it makes sense or follows logically to you, but not necessarily to somebody else. So everything we write down here has to be justified using these fundamental laws of logic. Direct reasoning, indirect reasoning, disjunctive simplification, whatever. All right, that's sort of making sense so far. This is a hairy kind of proof because you have to switch from these to that kind of conditional equivalence, and that's kind of weird. But we'll do some more straightforward examples. There's the basic approach making sense so far. So start with what you know, apply laws of logic, try to prove what it is you're trying to prove. That's the one sentence synopsis of the next week. All right, so let's do a word problem. Because playing with just these variables kind of gets old after a while. So let's do a word problem. So if you text me, I'll do my homework. Because apparently I don't remember to do homework on my own. So if you send me a text later on, I'll do my homework. If you don't text me, I'll go to sleep early. If I go to sleep early, I'll wake up refreshed. Therefore, if I don't do my homework, I'll wake up refreshed. Alright, so here's a claim I'm making. If you text me, I'll do my homework. If you don't text me, I'll go to sleep early. If I go to sleep early, I'll wake up refreshed. Therefore, if I don't do my homework, I'll wake up refreshed. And we want to know, is this a logical conclusion given these three statements above? Can we conclude this fourth statement from the first three? Right, so the therefore is kind of like that horizontal line. And if we take these three things to be hypotheses, can we logically prove that this conclusion is true? So somehow we've got to get this into this. We've got to turn it into this very formal language of propositional logic. So we need to write some propositional variables to represent all of this stuff, right? We got to get away from the words and get down to just good old symbols. So we need some propositions. Now I could make a proposition P which says if you text me I'll do my homework, and proposition Q says this, and proposition R says that, and proposition T says this, and then try to prove that PRQ gets me T. But that's not going to get me very far, right? To turn this into the language of propositional logic, we usually want our propositional variables to represent small propositions, as small as possible. So rather than say, let P be the proposition, if you text me, I'll do my homework, I would say, let's make a pair of propositions. One for you text me, one for I do my homework. And then let's write this as if that first thing, then this second thing. So let's do this. Let T be the proposition, you text me. And let H be the proposition, I do my homework. All right, so what would be some other propositions we could define to try to rewrite this theorem in the language of propositional logic? Do we need another variable for the proposition, you don't text me? Do we need to make a proposition like D for that? No, why not? Right, so we can just say not T, that's the proposition, you don't text me. All right, so somebody suggested let S be the proposition, I go to sleep early, so I like that. Let S be the proposition, I go to sleep early. All right, and somebody else suggested a proposition, you wake up refreshed. So let's use R for that. I wake up refreshed. And I think that gives us enough propositional variables to be able to write all of these statements using formal language. So let me start this on a new page. And what does this first statement say? If you text me, I'll do my homework. So that's just if T, then H. The second statement says if you don't text me, so I'm going to write these side by side and say this is what we want to prove. So given if you text me, I'll do my homework, and also given if you don't text me, I'll go to sleep early. Well, if you don't text me, that's not T. Then I'll go to sleep early. And if I go to sleep early, I'll wake up refreshed, so that's S implies R. Therefore, if I don't do my homework, that's not H. Then I'll wake up refreshed. So now we've taken this word problem and we've turned it into something like what we did a few moments ago, something which says, given this, prove that. Okay, in this case, given these things, prove that thing. All right, well, I'll start off the proof. All right, there's 3 starting lines for the proof. I've just restated the hypotheses. So what else can I do? What's another statement I could write down and why? All right, so someone said not T, then R. And why would that be true? Chain rule. All right. So we're told if not T, then S, and we're told if S, then R. So we can chain rule those together and say if not T, then R. And that's the chain rule 2 and 3. All right, good. We got if not T, then R.
You could do the contrapositive on 1 for not H. That is, if not H, then not T.
Okay, so suggestion, do the contrapositive on 1. Was that a random suggestion, or you got a plan in mind for where this is going?
Well, then you just chain rule it out.
Yeah. So you can do this by just kind of randomly doing things and see where it gets you, right? But it's a little bit like chess. At some point you might say, oh, you know, I'm trying to prove not H and I've got a not T. Oh, if I do the contrapositive, I'll have a not T on the right side, right? So let's go ahead and do that. Take the contrapositive, which says not H implies not T. That's the contrapositive of 1. And now we're all set up for the chain rule again. So not H implies not T implies R. So not H implies R. That's the chain rule of 5 chained together with 4. And guess what? We're done. Because not H implies R, that's what we were asked to prove. So there's an absolute airtight proof that given these 3 things, we can conclude that thing. So yeah, the key to waking up refreshed is don't do your homework. QED. All right. Solid advice. All right, so that's our basic plan for the next few days, is to develop our skills at doing these kinds of things, to look at ways that this can play out, to come back and look at fallacies. So we talked about a few fallacies already, denying the hypothesis and affirming the conclusion, and we'll avoid those where possible, but they're very close to direct reasoning and indirect reasoning. Right? Denying the hypothesis says that if P is false, we can't conclude not Q. So the formal statement of these fallacies looks like this. Right, so that's fallacy of denying the hypothesis. Right, so this does not follow from that. It could be that Q turns out to be false, right? But it could also be that Q turns out to be true. And then this is the fallacy of affirming the conclusion. And again, it could turn out that P is true anyway, we just can't conclude it. P could be false. All right, so things to pay attention to in doing proofs. 1, make sure you've written out what you're trying to prove. Make sure every statement you write is true, either because it's a hypothesis or because it follows from what you've written so far. Everything down to here in my proof must be true. Right? The only reason I write something down is because I know it's true or I've proven that it's true. Which means that the next line that I write can use any of these things above here and any laws of logic to prove that this is a true statement. What you can never do in a proof like this, though, is write down something that you don't know is true. If I were to put a line in here that said S or R, my proof is no longer valid, because I don't know that S or R is true. And anything that comes after that that depends on this could be true, could be false. It's only true if I know S or R is true. In particular, if I write down S or R, and I come down with a bunch of steps, and eventually I prove S or R, what have I proven? I've proven if S or R is true, then S or R is true. Well, that doesn't prove anything. Okay, we'll see examples of that too. But we avoid that by making sure everything we write down is known to be true. And then we list reasons why each of those things is true. And the last thing in our proof that we show to be true should be the thing we were asked to show is true. This thing over here in this case. And then we can write down that this last statement is what we were asked to demonstrate. That's what QED says. All right, the one time we're going to get a little bit away from this rule of never writing this down is what we call an indirect proof. And in an indirect proof, we're going to assume that the conclusion is true. We're going to assume the conclusion is false, and we're going to find a contradiction. And that's going to force us to conclude that the conclusion must have been true. And that can tangle up our notion of never writing down something that we haven't proven yet. So I want you to think about direct proofs for a couple of days. And then Wednesday, we'll look at an indirect proof. And we'll be really careful how we do that, because we will write down things that we haven't proven. There'll be assumptions. And we can write down an assumption as long as we understand that everything after that is only true if that assumption is true. Right? That's what we're doing with hypotheses. We don't know that P implies R. But we're saying if this is true, and this is true, and this is true, then all of this follows. And that's all we're proving. We're not proving P implies R. We're not proving S or R. We're proving if this, this, and this are true, then that is true. Okay? All right, so we're good for that. I will see you next time. Have a good afternoon. Enjoy the sun. Go for a run. I'll catch you next time. Thanks.